Imagine continents. Those seemingly immovable land masses are actually shedding pieces of themselves into the ocean depths, triggering volcanic eruptions in unexpected places. This groundbreaking discovery is forcing geologists to rethink how our planet's interior actually works. It's not just about plate tectonics anymore. For years, scientists have been baffled by a strange phenomenon: volcanic islands in the middle of the ocean containing rocks with a distinctly continental chemical fingerprint. How does rock from the continents end up in oceanic volcanoes? It's a geological mystery that's finally being solved. The traditional view of continents as static blocks is being challenged. Instead of surface drifting, this new research reveals that fragments break off from the underside of continents and slowly sink into the oceanic mantle. That super hot, mostly solid layer beneath the seafloor. Think of it like a slow, geological shedding process. This revelation, detailed in a study led by Professor Thomas Jernon at the University of Southampton and published in Nature Geoscience, offers a compelling explanation for the unusual chemistry of certain ocean volcanoes. But here's where it gets controversial. Does this mean our understanding of mantle dynamics is fundamentally flawed? When you picture volcanoes, you probably envision dramatic eruptions along tectonic plate boundaries, where Earth's massive plates collide or separate. However, numerous volcanic islands exist far from these active zones, defying conventional explanations. Christmas Island, situated in the northeast Indian Ocean, is a prime example. Its lava contains enriched elements typically associated with continental rocks, not oceanic ones. Previously, geologists proposed that ocean sediments, dragged deep into the Earth during tectonic plate subduction, were the source of this peculiar chemistry. Others suggested mantle plumes, rising columns of hot rock originating from the planet's deep interior. But neither theory fully accounted for the evidence. And this is the part most people miss. Some of these ocean volcanoes lack evidence of recycled crust, while others are too shallow or cold to be plume-driven. Something simply didn't add up. So what's the real explanation? The answer, according to researchers, lies in a slow but immensely powerful process occurring deep beneath the continents. When continents begin to break apart, as happened when the ancient supercontinent Gondwana fragmented over 100 million years ago, the effects aren't confined to the surface. The breakup sends waves of stress deep into the underlying mantle. These stress waves can strip away portions of the continental base, reaching depths of up to 125 miles, and drag them sideways into the oceanic mantle. This process is incredibly slow, progressing at a rate 1,000,000 times slower than a snail's pace. However, over tens of millions of years, these detached chunks can travel hundreds of miles. Once these continental fragments are embedded within the oceanic mantle, they become incorporated into the magma-generating machinery that fuels ocean volcanoes. Professor Jernon aptly stated, "We've known for decades that parts of the mantle beneath the oceans look strangely contaminated, as if pieces of ancient continents somehow ended up in there. But we haven't been able to adequately explain how all that continental material got there." To investigate this phenomenon, the research team created sophisticated computer simulations that mimicked the behavior of Earth's mantle during tectonic breakups. The models revealed that continental rifting creates instability deep below, generating a ripple effect along the base of the continent. This ripple, termed a mantle wave, propagates outward, peeling off fragments of the continental root and sweeping them into the surrounding oceanic mantle. Sascha Brun, a co-author of the study from the GFZ German Research Center for Geosciences, explained, "We found that the mantle is still feeling the effects of continental breakup long after the continents themselves have separated. The system doesn't switch off when a new ocean basin forms. The mantle keeps moving, reorganizing, and transporting enriched material far from where it originated." The team focused part of their research on the Indian Ocean Seamount Province, a chain of underwater volcanic mountains that emerged after the breakup of Gondwana. Their study demonstrated that shortly after the breakup, magma rich in continental elements surged upward from below. Over time, this signal diminished, suggesting that the source material had ceased to arrive. Importantly, this occurred in the absence of a deep mantle plume, the usual suspect. This implies that an alternative mechanism, such as the one depicted in the simulations, must have been responsible. We're not ruling out mantle plumes, but this discovery points to a completely new mechanism that also shapes the composition of the Earth's mantle. Jernon clarified. Mantle waves can carry blobs of continental material far into the oceanic mantle, leaving behind a chemical signature that endures long after the continents have broken apart. This isn't the first time this research team has linked mantle waves to significant planetary shifts. Their previous work indicated that these slow, deep motions might trigger diamond eruptions and reshape landscapes far from tectonic boundaries. This new study adds another crucial piece to the puzzle of how Earth operates from the inside out, highlighting the enduring role of ancient continental remnants in shaping our planet today. Ultimately, this research suggests a far more dynamic and interconnected Earth system than previously imagined. Continents aren't just passive land masses. They actively contribute to the composition and behavior of the Earth's mantle, influencing volcanic activity in unexpected ways. What do you think about this new perspective on continental dynamics? Does it change how you view the Earth's interior? Could this discovery lead to new ways of predicting volcanic eruptions? Share your thoughts and questions in the comments below.